Dear students, welcome back to the video lectures on Advanced Digital Signal Processing course. In the previous video lecture, we have discussed on frequency domain implication of the downsampling operation. So let us resume back our discussion with more examples and also understand the implications in reconstruction ability when we do downsampling, and what should be the measures to take to make effective reconstruction even after downsampling by a factor m. So in the previous video lecture, we have seen that if you want to reconstruct the signal back with fm being the maximum frequency in the signal and m being this downsampling rate after after a initial sampling by fs, what we need is the sampling frequency has to be chosen such that it has to be greater than m times the maximum frequency, twice the maximum frequency in the signal. This will avoid aliasing even after downsampling and enable us to reconstruct the signal back. Now let us see for the example that we have taken, can we increase the downsampling rate more than 2 here, which we have discussed in the previous example, previous video lecture. So see, assume that fm is 500 and if we consider m to be 3, then what does happen? 3 into 500 into 2, that is 3000, which is the lesser than, which is higher than the fs that we have taken here. Thus, if we sample with 2000, fs being 2000, we will not be able to reconstruct if we want to downsample by 3 times. We can only reconstruct back the signal if we downsample by 2 times when fs is 2000 and fm in the given signal is 500. Okay, so this indicates clearly that we should do something else or something more to enable us to avoid aliasing and reconstruct back the signal even with partial details when downsampling rate is higher. Let us for a further discussion, let us consider the case when the downsampling rate is 3, right? So take the same example where you have the xc of j omega with omega m being 2 pi 500 into 2 pi, that is fm being 500 h, and the signal xc of t is being sampled with fs equal to 2000, and the sample signal xn has the spectrum given by x of e power j omega as given by this. Please note that the spectrum I have given here is explicitly x of e power j omega, which in the previous discussion what we had given is excess of j omega. Okay, that is in the omega by 2 pi scale, right? Continuous time frequency, continuous discrete time, continuous time Fourier transform frequency, okay, or continuous frequency, right? This corresponds to discrete frequency or the frequency from the discrete signal. Okay, so this corresponds to discrete time Fourier transform. Thus, you can see the spectrum of discrete time Fourier transform of x of n, that is x of e power j omega here, right? So now, if we assume that if we want to downsample by 3 times, which is shown here, so what should we do? We can we will write xd of e power j omega as L ranging from 0 to 2, summation is from 0 to 2, x of e power j omega minus 2 pi L by m. This comes from the expression that we have derived in the previous class, right? So if we do downsampling, it has the same operation as sampling, where convolution with impulse train makes the sampled spectrum to repeat at each of the impulses in the frequency domain. Similarly, if I downsample by 2 times, the spectrum xd of e power j omega repeats 2 times. If I sample for 3 times, it repeats for 3 times. Okay, so and at spacing of 2 pi, right? So as you can see here, omega minus 2 pi L by m. That means the spacing between each of the repetitions of x of e power j omega x is in xd of e power j omega is 2 pi, right? So now let us sketch with this understanding. Let us sketch the spectrum of downsample signal, right? And this be the spectrum in minus pi to pi range. Please note that if you, this is x of e power j omega and periodic with 2 pi. So whatever you get the spectrum here will repeat for each at each 2 pi, right? And this is the next repetition. We will try to see its implication here in xd of e power j omega. So let us now sketch the spectrum for xd of e power j omega. Okay, xd of e power j omega, right? So let the right. So let us first mark the axis. This is omega, small omega axis. So this is pi. This is pi by 2, and this is, sorry, this is 0. This is pi by 2. This is pi, and then this is 3 pi by 2, right? And this is 2 pi, correct? And this is 5 pi by 2, and this is 3 pi, and this is 7 pi by 2, and this is 4 pi, right? And then this is what? 6, 7, 5 pi by 9 pi by 2, or 4.5 pi, right? Pi by 2, and this is what? 6 pi, okay? And this is 11 pi by 2, or 5.5 pi, and this is 8 pi, right? Sorry, 7 pi. Okay, pi, 0, pi, 2 pi, 3 pi, 4 pi, this is 5 pi, sorry. Okay, this is 4.5 pi, and this is 5 pi, right? This is 5 pi. Okay, this is 5.5 pi. Okay, let us write in 5.5 and so on. It is easy for us. This is 5.5 pi, and this is 6 pi. Okay, so up to this is, say, 6.5 pi. Okay, up to here let us see, right? So first, let us mark few things in the other direction as well. Minus pi by 2, and this is minus pi. Okay, and this is minus 1.5 pi. Okay, and this is minus 2 pi. Okay, and this is minus 2.5 pi. Okay, and finally that is actually minus 3 pi. Okay, right? So yeah, minus 3 pi. Okay, this point, last point. Okay, so now let us sketch the first base spectrum. What will happen to this? Okay, to this. What does it happen? As you can see in the expression, there are two things as we discussed before. One is stretching by 3, because as you see, downsampling operation makes the x of n to xd of n compress in time domain, and hence in frequency domain there is an expansion for small omega axis, right? So and hence you can see in xd of e power j omega there is a stretch, okay, or a expansion by 3 times. So pi minus pi by 2 to plus pi by 2 goes to minus 3 pi by 2 to plus 3 pi by 2. That is minus here 2, right? And plus 3 pi by 2. This is the first spectrum, right? Now, where is the repetition? First repetition of this base spectrum happens. Let's show with slightly different blue. Okay, so where does the repetition of this base spectrum happens? From at 2 pi. So it has to repeat, because you can write here omega minus 2 pi L equal to 1 by 3. So it should be repeated at omega minus 2 pi, that is at pi 2 pi, and it has again to be stretched by 3. So stretched by 3, and it has to be repeated at 2 pi. So it has to be centered at 2 pi and stretched by 3. So minus, it is from pi by 2, okay, pi by 2 to where? 7 pi by 2. Okay, so because the stretch spectrum is 1.5 times. Okay, so it is up to 7 pi by 2 or 3.5 pi. Right. Okay, this is the next spectrum. As you can see, if you want to write it, this is x of e power. Okay, let us write with same color. Finally, we will write with same color. And let us figure out another, say, let us take this color. Okay, third replica, where does it occur? 2 pi by 2 pi 4 pi. Okay, omega minus 4 pi by 3, where L equal to 2. So it has to come at 4 pi. So at 4 pi, it has to come 4 pi minus 3 pi by 2 to 4 pi plus 3 pi by 2. Okay, so that is from here, it goes up to 4 pi to where 4 pi plus 3 pi by 2, that is 5.5. Okay, these three are the replicas of the base spectrum, right? As you can see, this is x of, so let us write now with some color. So which, say, let us take this color, x of e power j omega by 3. Okay, this is the first stretch of the base spectrum, plus what is this, x of e power j omega minus 2 pi by 3. This is the second, okay, let me j omega minus 2 pi. Okay, this is at 2 pi plus, what is the third one? Third one is x of e power j omega minus 4 pi by 3, right? Okay, third one. These three put together is given as, okay, is given as what? Is xd of e power j omega. Is that all? Xd of e power j omega? Ideally, this is all. Okay, but however, the spectrum at 2 pi also keep repeating from at 6 pi. Okay, also minus 2 pi also keep repeating from there. So there you can see the like you can see the spectrum at, for example, at 2 pi. Where does it first occur? So let us sketch with black itself. At 6 pi. So where does it occur? 6 pi minus 3 pi by 2 to 6 pi plus 3 pi by 2. So from 6 pi minus 3 pi by 2, that is from here, right, to 6 pi plus 3 pi, that up to 7.5 pi. Okay, we will just leave it. Okay, it's up to 7.5. Okay, similarly, it will have two more replicas, right? In the similarly, you can see the spectrum that is here. Okay, so let's denote this also with slightly different color to have a better understanding. Let us put this color. Okay, so this one, this is this color. Okay, so it is from minus 5 pi by 2, sorry. Right, so right. So this, now where does this occur? Its replica will be there at, say, minus 2 pi. So it will start from minus 6 pi. Okay, and it minus 6 pi is first its replica in this other direction, but it will also have at minus 4 pi, but it's minus 6 pi plus 2 pi, minus 6 pi plus 4 pi. So it minus 2 pi, minus 4 pi, minus 2 pi also it will have a replica. This will have a replica at, okay, minus 6 pi, okay, minus 4 pi, and minus 2 pi in xd of e power j omega, right? Okay, so we'll only sketch at minus 2 pi. So from where to where it will go? Minus 2 pi, that is minus 3 pi by 2. Okay, 2 it will go. Okay, it will go. Right? So you can see like this. This is the, so these first, you can see that from here to here. Okay, these are all the spectrums corresponding to okay, the base spectrum that you have from minus pi by 2 to pi by 2, right? So, right. Okay. So, but what has happened in this process of downsampling by 3 times? As anticipated, there is aliasing. Okay, why does there is aliasing? Why did we anticipate for aliasing? Because as you can, we have discussed. So in case if we have a sampling maximum frequency in the signal being 500, okay, FM, then Fs to avoid aliasing after downsampling by m times is 2 times Fs. FM, right? Because this is actually the if we directly downsample, this has to be, and to avoid aliasing after downsampling, the condition is Fs has to be at least 2 times FM, right? But if I know that I will be downsampling by m times, or even if I initially downsample by initially sample with Fs and downsample by m times, then Fs dash to avoid aliasing has to be greater than, okay, m times, find m times Fs. Okay, it has to be greater than m times Fs, right? That is not satisfied here in this situation. Okay, or okay, say m times Fs, right? So this is not satisfied in this situation. Why? You can see that m equal to 3. Okay, m equal to 3 times f 1000. Okay, is, but whereas this is Fs dash has to be greater than 3000. Okay, but however, we have taken Fs equal to 2000. Thus, we know that aliasing happens. And now you can see that this is the aliased region. So non-aliasing, like if we want to avoid aliasing, okay, what should we do? That is the next question. There is an aliasing that we have anticipated and it has happened. Now we assume that we want to avoid aliasing. Okay, what do you think we should do? Okay, what should we do? We can say that, see, if we, anyway, we know that 3 times we are trying, we wanted to upsample, right? So downsample. So to avoid aliasing after downsampling, right? So the spectrum has to be from minus pi to pi. Okay, so whatever is the base spectrum, this base spectrum, okay, after stretching by m times, okay, m times the omega, if I consider this as omega m, okay, in the discrete frequency domain, okay, then this omega m into m, that is because I will be downsampling by 3 times, has to be equal to pi, right? If this is only up to pi, then what does it happen? Similarly, the other spectrum at 2 pi also will stretch only up to pi, right? And my pi to 2 pi, this will stretch only from minus pi to pi. So I need to limit even after downsampling. If you want to avoid aliasing, the condition is that omega m has to be, or omega m is pi m is equal to pi, or omega m has to be lesser than, right, how much? Pi by m. Okay, to avoid aliasing. Avoid aliasing. Okay, right? So now this is the condition to avoid the aliasing. Now, see, if it doesn't happen, then what should we do to avoid aliasing? Assume that FM is fixed. Because of FM being fixed, omega m is also fixed. However, in some application, we are demanded to do downsampling by m times. Now, to avoid aliasing, what should we do? That's the question, right? What should we do? See here, pi by m is how much? If you want to do downsampling by 3 times, pi by m is pi by 3. So if only the frequencies that you have from minus pi by 3 to pi by 3 will only be retained. and remaining frequencies, anyway, you know that they get aliased or mixed with other frequencies. So to avoid aliasing, okay, what can we do is we can have a filter initially from the in the frequency, in the discrete frequency domain, or say for the spectrum ranging from discrete time Fourier transform spectrum ranging from minus pi by 3 to pi by 3. Okay, so that will help us to avoid aliasing. So you may have a spectrum like so. This is, assume that this is minus pi by 3 and this is up to pi by 3. Okay, so this is minus pi by 3. This, if I apply this spectrum, this is anti-aliasing spectrum I can call. Okay, so this filter is an anti-aliasing filter. Okay, I may call it as anti-aliasing. Okay, filter J e power j omega. Okay, so this anti-aliasing filter, if I apply, such that the filter is from minus pi by m to pi by m. Okay, then it will avoid subsequently aliasing when even if I downsample by m times. Is that clear? So let us move on and see now. In if I do that, will it suppress the aliasing or not? Okay, now let us start directly from x of. Okay, let us directly start from x of e power j omega. Right? So take the same example that we had taken and let us start from x of e power j omega. Okay, so now assume that we retain the scales, so we keep the same scales. Okay, as before. Right, this, let this be 0, minus pi by 2 and pi by 2, right? And then here minus 2 pi and plus 2 pi. Okay, so now what should we do? Let us assume that we want to do now filtering before. Okay, before we, this is x of n given and corresponding x of e power j omega drawn here, and we know that we want to downsample by 3 times. Okay, we know a priori by m times, that is m times. Okay, we know a priori to get xd of n. Now see, this is small omega x. To avoid aliasing, what did we say? The maximum frequency led in the signal into m has to be equal to pi or less than or equal to pi, right? To avoid aliasing. Avoid aliasing after downsampling by m times. What the condition we need is omega m into m is less than or equal to pi. Okay, this is the condition needed, where omega m is the, where omega m is maximum frequency, discrete frequency in x of n. Okay, in discrete time signal x of n, right? So this is the condition needed, right? So, but say if you want to do downsampling by 3 and omega m is pi by 2, it doesn't meet this condition. And hence, to avoid aliasing, what you need is to apply a low pass filter. Okay, for omega m equal to pi by 2 and m equal to 3. Okay, this condition is not met. Okay, thus we need to apply a filter with cutoff frequency. How much? Pi by m. Okay, before filtering, before downsampling. Right? Why should we apply before downsampling? Because then only we can limit the aliasing, right? Because after downsampling, anyway, all gets aliased if the condition is not satisfied. Correct? So to avoid aliasing, you should apply, this is known as, this is referred to as anti-aliasing filter. Filter. Okay, so what we do now? So let see, this x of n is sent through a filter. Which kind of filter is this? This is a discrete filter. Okay, since we have named it as XA, HA, discrete filter will send, and what we get, output is, so X filtered, so anti-alias filters. So X filtered, let us write. Okay, of n. Right, and for this you can apply, okay, downsampling by 3 by m times. Okay, and this xd of n, okay, will not have aliasing, right? And this filter cutoff frequency is minus pi by m to pi by m to limit the spectrum even after downsampling to minus pi to pi range, right? And this spectrum, if you apply this limit, this spectrum will be only from minus pi to pi. Okay, then when you consider about the this minus pi to pi range, same thing happens in the expanded spectrum. Okay, in pi to 2 pi range and so on, right? Okay, so this is cutoff frequency, low pass filter. This is referred to as low pass filter because pi is maximum frequency or high frequency and 0 is low frequency in minus pi to pi range. Okay, right, and this is referred to as low pass filter. That's right, it passes the frequencies, low frequencies, okay, from minus pi to pi range. Okay, this spectrum looks like, so it is looks like now, right? It looks like this. Okay, it looks like this. Okay, it looks like this. Minus pi by 2, minus pi by 3, pi by 3 range. Okay, and the height probably is 1, we can put. Okay, this is h of, how much? H E of e power j omega. Right? Right. So we should multiply them in frequency domain. Right? So now in frequency domain, what happens? X f of e power j omega is equal to x of e power j omega into h of e power HA of e power j omega. Okay, and this h of HA of e power j omega is defined as 1 for minus pi by m2, okay, pi by m, okay, 0 else. Okay, small omega ranging from, we can also denote usually with mod omega less than pi by m. Okay, this whatever we define here, please note that these definitions are from minus pi to pi range only. Okay, because the spectrum anyway is periodic with 2 pi, discrete time Fourier transform spectrum. So we don't bother to define in rest of the region. Okay, so now let us see the sample spectrum in minus pi to pi range. Let us sketch the sample spectrum in minus pi to pi range. Minus pi to minus pi, okay, 1, 2, 3, 4, okay, pi range, and this is 0. right? So how does it look like? It looks like, see, this is being cut here. So you will see only from, let me sketch with this color or this color. Okay. So you can only see from up to here, minus pi by 3 to pi by 3. Okay. In this range only you will see. And how does the spectrum look like? Okay. And then it goes. Sorry. Right. And this straight comes here. Okay. So this is how this clipped or like a tapered spectrum. Okay. So minus pi by 3 to pi by 3. And this is, you can, based on our namings or notation, we have xf of e power 0. Now what will happen? This again repeats at 2 pi, minus 2 pi and so on. That is the, and now if I do downsampling on this by 3 times, you can see that there will not be any aliasing. Let us see, let us complete that that discussion of downsampling, this filtering by 3 times after filtering. Okay, so I will directly sketch here x of xf of e power j omega, right? So let us sketch this. Okay, so now 0 let it be here, pi by 2, pi 3 pi by 2 and 2 pi and 2.5 pi, and this is 3 pi, 3.5 pi, 4 pi, and so on. Let us minus pi by 2, minus pi, minus 3 pi by 2 and minus 2 pi. Okay, so let us sketch the spectrums. The base spectrum let us sketch first. Okay, so it is from 3 pi by 2. Okay, right. So this you can see, right? So you can see that this is from minus 3 pi by 2, minus pi by 3, sorry, minus pi by 3 to pi by 3. Okay, and this is the base spectrum, right? And now what, around 2 pi, what does it happen? Same filtering will happen around 2 pi, and hence the spectrum will be from here to here. Okay, and its height is also same, and hence this is from so 2 pi minus pi by 3 to 2 pi plus pi by 3. Okay, that I'm leaving it here. So this is 2 pi plus pi by 3. Okay, similarly 2 pi minus pi by 3. This is clear. So on the other hand, this side, what does it happen? Same thing will happen. So yeah, and hence spectrum is up to here. Okay, so this spectrum is also from minus 2 pi, minus pi by 3, and minus 2 pi, minus 2 pi plus pi by 3, right? So let's now sketch. Let us assume that this is xf of n, and we want to downsample this by 3 times now. What is this? This is excess of f of n is after and applying anti-aliasing filter. Okay, and now we want to do downsampling. So this is what we are doing now. Instead of directly downsampling, we are applying a anti-aliasing filter and then downsampling. Okay, so this is the usual procedure. because in most of the cases, whenever we do downsampling, there is a possibility or a risk that the aliasing may happen after downsampling, right? So to avoid that, it is customary, or it is most of the times it is important and needed to apply a low pass filter of bandwidth minus pi by 3 to or minus pi by m to plus pi by m, right? That will avoid aliasing after downsampling. Okay, this we are doing downsampling in discrete domain, and hence the filter is also in discrete. We are nowhere going back now into continuous time domain, right? So this is a discrete filter. Please note that. Now we want to do downsampling and get xd of n, right? So let us sketch the spectrum now. Right? So see what will happen to the base spectrum. Let's sketch with same colors. So it gets stretched by 3 times, and hence it goes from minus pi by 3 into 3. So it is minus pi to pi. So this is okay. We need to keep minus 1 point pi by 2 and pi minus pi, and hence this is minus 1.5 pi, and this is minus 2 pi, and this is minus 2.5 pi. Okay, and this is minus. Okay, so similarly, let us write this side as well. Pi by 2 and pi, and this is 1.5 pi, and this is 2 pi, and this is 2.5 pi, and this is 3 pi, and this is 3.5 pi, and this is 4 pi, and this is 4.5 pi, right? And then anyway, 4.6 pi. Okay, 3.5 for 4.5, 5.5 pi, and then this is 6 pi. Okay, this is the spectrum. Now let us sketch the base spectrum. That is, say, minus pi to pi. So same thing will happen here. Minus pi to pi. Okay, minus pi by 3 to pi by 3, whichever we had here will get stretched. Right? And this is from minus pi to pi. We can see here. Right? And okay. So, and then where does the second spectrum look? It, see, this has to repeat, right? So where does this repeat? Again at 2 pi. Once it repeats at 2 pi, and again it goes from minus pi to pi. So 2 pi minus pi to 2 pi plus pi. And hence its replica, you can see that its replica will come from minus 2 pi to 2 pi minus pi to 2 pi plus pi, right? This is the second like replica of the base spectrum, right? And then where does the next replica come? Where does the third one will come? It is from 4 pi, right? Plus pi, 4 pi minus pi to 4 pi plus pi. And hence this is from here to till here, right? And these are the 3 replicas of the base spectrum. Now, where does the spectrum corresponding to this green one looks? At 6 pi. And hence it comes here, right? And then it goes like this. Similarly, it will have its 3 replicas. So, and so what you can see here is similarly the black one, it will have its replicas, and one replica will come from around minus 2 pi. That is up to minus 2 pi, minus pi to minus 2 pi plus pi. It is from here to here. So by if I apply this anti-aliasing filter, it avoids the aliasing just by just avoids aliasing. Since I have applied anti-aliasing filter of minus pi by m to plus pi by m. Okay, it just avoids aliasing. In fact, you can see that these are all actually magnitudes. So in fact, you can oh fine, I don't know whether, yeah, fine, okay. Oh, okay, so I will try to sketch the baseline again. Let us sketch with a slightly different color. Right. Right. Okay, so you can see this is oh, this is gone. Right. So you can see that this minus pi, pi, 2 pi, 2.5 pi. Oh, I think this is 3 pi. Sorry. Pi. And this is 2.5 pi, 3 pi. Okay, and this is 5 pi. Right, you can see that this is how it happens. So this is now xd of e power j omega. So x of e power j omega by 3. Okay, this is xf you should write, plus xf of e power j omega minus 2 pi by 3 plus xf of e power j omega minus 4 pi by 3. Right, these three put together will give us xd of e power j omega. Right, that's what has happened here. Right, so you can see that aliasing can be avoided if we apply an anti-aliasing filter. So in general, if you want to avoid aliasing for any of the sample signal, already sample signal, you should apply a low pass filter. Okay, of cutoff frequency minus pi by m, 2 pi by m. Okay, and then apply downsampling by whatever downsampling m you wish to do. And this xd of n may or may not have the whole information of x of n, but there will be no aliasing, right? So this indicates that this enables, so this is referred to as anti-aliasing filter. Okay, so x d of n may or may not have all info or of say x of n, but will have, okay, what? No aliasing because of anti-aliasing filter. Okay, right. So this is what to be taken care while downsampling the signal x of n. So directly from discrete domain to discrete, another discrete domain signal, right? Thank you. So we will discuss in the next video lecture on how what need to be, like how does the spectrum vary in upsampling, and what is there any care needed for filtering before or after upsampling. Thank you.